The Puget Lowland is known for its scenic coastlines, bustling urban ports, and rich farmlands to the south. The natural resources and the geologic history of the Puget Sound and surrounding areas have helped to shape the history of the state of Washington. The modern landscape of the Puget Lowland is only the most recent in a long lineage of interglacial settings which have evolved here over the last 2 million years. This particular version represents a fairly radical change from the last Olympia age interglacial period in that it includes a fairly large body of marine water, the Puget Sound, and comprises a somewhat more diverse topography. This is owed to two key aspects of this most recent glacial advance. These include the deposition of an extensive set of pro-glacial sediments and the large-scale erosion of those sediments as the glaciers rapidly retreated from the basin. Most of the information presented in this lecture was obtained from a paper entitled The Glacial Origins of the Puget Basin, the Evolution of the Modern Lowland Landscape by J. Figg, 2008. The Puget Lowland region is a wide, low-lying area between the Cascade Range to the east and the Olympic Mountains to the west. The region extends from the San Juan Islands in the north to past the southern end of the Puget Sound. The Puget Sound region is a vast lowland basin nestled between the Cascade and Olympic Mountains, an inland maritime province of over 10,000 square miles. Its center is occupied by the Puget Sound, a marine body of irregular design, featuring over 2,000 miles of coastline. This inland sea surrounds a number of north-south trending islands and peninsulas and receives the flow of a dozen major river systems draining out of the adjoining mountains. It is a complex hydrologic, climatologic, and ecologic system of very unique qualities. Along its shoreline, it is home to some 3.5 million people. A wide variety of rock types can be found in the Puget Lowland. A curious observer will find rocks that have formed from ancient volcanoes similar to that of Mount St. Helens and Mount Rainier. There are even metamorphic rocks that have formed under the extreme temperature and pressures that are caused by the force of plate tectonics. Some of the metamorphic rocks of the San Juan Islands were accreted to North America over 160 million years ago. Some of the oldest marine sedimentary rocks in the area date back almost 400 million years. The most abundant and widespread geologic units in the Puget Lowlands are not actually rocks, but sediments that are patiently waiting to become rocks. These sediments were left behind by glaciers that advanced as many as 5 times into the Puget Sound area within the last 2 million years, most recently about 15,000 years ago. Most of the rocks in the basement below the lowlands are the same rocks comprising the western domain of the northern Cascades. They consist of sedimentary and volcanic rocks making up the various terrains that docked onto North America between Precambrian and early Cretaceous. We currently have evidence for 6 episodes of continental glaciation in the Puget Basin. These include the 2 million year ago Oregon Glaciation, the 1.6 million year ago Stuck Glaciation, the 1 million year ago Salmon Spring Glaciation, the 250,000 year ago Double Bluff Glaciation, the 80 to 60,000 year ago Possession Glaciation, and the recent 18 to 12,000 year ago Fraser Glaciation. These periods of glaciation were separated by non-glacial intervals with conditions most like the present. The older non-glacial periods likely also include numerous glacial episodes. The till deposited during the Orting Glaciation is exposed near the town of Orting in the Puyallup Valley. It sits atop streambed deposits of rivers draining off the Cascade Mountains and lies beneath non-glacial sediments known as the Alderton Formation. It is thought to be about 2 million years old, and it is the oldest known glacial deposits in the Puget Basin. Atop the Alderton Formation is another layer of till, 2 layers actually, which represents the Stuck Glaciation of about 1.6 million years ago. Limited evidence suggests that this episode may have dammed the Puget Basin, forming a large lake here. This till layer underlines a non-glacial unit known as the Puyallup Formation. The Puyallup has a distinctive layer of river-laid sand at its base, but most of it consists of debris brought down from Mount Rainier in the form of mud flows and river deposits. The till of the Salmon Spring Glaciation is exposed in the Puyallup Valley east of Sumner. It consists of glacial outwash gravel and till. It overlies a distinctive ash deposit from the Mount Baker area, a deposit dated at about 1 million years old. Between the 1 million year age Salmon Spring episode and the 250,000 year age Double Bluff episode, the record is unknown. There are likely several glacial episodes over this span of time. Till of the Double Bluff Glaciation is the oldest glacial deposits which can be found in a number of locales around the basin. The classic exposure is on Double Bluff Beach on the south end of Whidbey Island. This till overlies a 6-meter gravel layer which is interpreted to be a proglacial outwash plain. The till layer itself is about 12 meters thick. Above the Double Bluff till lies non-glacial sediments of the Whidbey Formation. The Whidbey Formation includes silt and peat sections, but is largely a fine sand showing evidence of deposition by a west-flowing river. The river was likely the ancestral Skagit. The Whidbey Formation, the Possession Till, the Esperance Sands, and the Vashon or Fraser Till can be found on the shores of Penn Cove, Whidbey Island. These sediments argue against a marine setting in the basin at this time. Pollen samples from the peat beds reflect a climate similar to or slightly cooler than exists at the present. The 60,000 or 80,000 to 60,000 year age Possession Till overlies the Whidbey Formation directly without intervening outwash deposit. It is best exposed at the Possession Point on the south end of Whidbey Island, but can be found in numerous other places, including in Seattle. On Whidbey Island, it consists of a layer of till without any intervening outwash deposits lying on the Whidbey Formation. It is only preserved locally and in many places is simply represented by an unconformity between the Whidbey Formation and younger sediments. Above the Possession Till lie the Olympia Beds, accumulated over the last non-glacial interval between 60 and 20,000 years ago. The Olympia Beds outcrop around the Puget Basin and consist of fluvial sand and silt deposit and lacustrine silt and clay beds. Interestingly, none of the outcrops reflect a proximity to a marine setting, suggesting that there was no Puget Sound over this period. Instead, the region was a low-lying river basin. Pollen samples from peat deposits in the Olympia Beds reflect a climate similar to or slightly cooler than our current interglacial conditions. The Whidbey Formation is exposed at Double Bluff on Whidbey Island. The inset photo shows cross-bedded sandstones that reflect deposition by a large west-flowing river, presumably the ancestral Skagit River. This photograph shows outcrop of the Whidbey Formation, the Possession Till, the Esperance Sand, and the Vashon or Fraser Till on the shores of Penn Cove, Whidbey Island. This photograph shows the Olympia Beds exposed along the shoreline at Discovery Park. The Olympia Beds date from 50,000 to 17,000 years ago. The Olympia Beds accumulated over the last non-glacial interval that occurred between 60 and 17,000 years ago. The beds outcrop around the Puget Basin and consist of both fluvial sand and silt deposits and lacustrine silt and clay beds. Interestingly, none of the outcrops reflect a proximity to a marine setting, suggesting that there was no Puget Sound over this period. Instead, the region was a low-lying river basin. Pollen samples from peat deposits in the Olympia Beds indicate a climate similar to or slightly cooler than our current interglacial conditions. Several major fault zones traverse the province, including the Seattle Fault, the Tacoma Fault, the southern Whidbey Island Fault, and the Darrington Devils Mountain Fault Zone. These faults are capable of producing earthquakes and lie within densely populated areas. Because of the hazard earthquakes along these fault zones pose to the public, they are being studied to determine their full extent and potential hazards. The growing use of LIDAR and geophysics, as well as continued detailed geologic mapping, result in new faults being discovered in the Puget lowland every year. While glaciers have been changing the landscape of the Puget Basin for the last 2 million years, they have not been responsible for the overall geomorphology of the region. It is a common misconception that glaciers carved out the Puget Basin as they advanced south into our province. The Puget Basin existed for millions of years before the glaciers first advanced over this landscape. Prior to about 5 million years ago, the entire Olympic Peninsula was a shallow marine province, and the western coastline fell along what are now the western foothills of the Cascade Mountains. With a change in the relationship between the continent and the oceanic Juan de Fuca Plate to the west, this setting began to evolve about 5 million years ago. Since that time, compression along the western edge of North America has raised a parallel set of folds along the continental margin. The western of these comprise the Insular Mountains of Vancouver Island, the Olympic Mountains, the Wallowa Hills, and the Oregon Coast Range. The eastern of these is the Cascade Range. The ranges have only been rising for about 5 million years and are among the youngest on the planet. Between the rising Olympic and Cascade Mountains, the Puget Basin is formed as a deep trough or syncline between these two folds on the continental margin. As those mountain ranges rise, the Puget Basin sinks beneath them at a rate of a bit less than half a millimeter each year. This setting was well established some 2 million years ago when the glaciers started advancing on this landscape. This illustration shows the extent of the Puget lobe of the Cordilleran ice sheet during the latest ice advance. Glaciers are ice sheets that can be thousands of feet thick and are exceptionally proficient at transforming landscapes. It was during the Vashon Stade, the latest ice advance and retreat about 15,000 to 12,000 years ago, that the Puget lowland got the extreme makeover that we see today. As glaciers scour the landscape they flow over, the sediment is collected and transported within, beneath, and above the ice. Glaciers are capable of moving the smallest of clay particles to very large boulders. Sediment is also transported in milky, silt-laden meltwater streams in front of the glacier's toe. In addition, the glaciers left behind many features in the landscape. Glaciers typically first develop in the high mountains where snowfall is abundant. In their accumulation zones, alpine glaciers are powerful erosive agents. Rocks entrained in the ice carve deep cirques in the mountain slopes as they flow downhill. Where the ice extends down into a valley, the erosive forces of the glacier carve it into a deep U-shaped trough. If conditions are sufficient, the ice can extend out of the mountain valleys and spill out onto the lowlands, where it broadens into a wide Piedmont glacier. There it deposits its load of suspended boulders, sand, silt, and clay onto the landscape. Carried further, those glaciers then coalesce into large continental-scale ice caps, which blanket the landscape. These can accumulate to thousands of feet in thickness. This is the process by which the Cordilleran ice cap has repeatedly formed in western Canada, as glaciers in the Insular, Coast Range, and the northern Rocky Mountains have coalesced into massive continental-scale features. Glaciers are conveyor belts of ice constantly flowing forward and transporting the load of boulders, sand, silt, and clay, which they quarry from their headwaters. Where this debris is deposited, these are known as moraine deposits. They are unique in their composition, lacking in any degree of sorting or stratification. Moraines accumulate along the margins of the ice where the glaciers grind against valley walls. These are lateral moraines. Medial moraines occur where two glaciers coalesce. If the end of the glacier holds a stable position for some time, it will accumulate a terminal moraine in front of it as the glacier retreats. The effect of ice advancing into a lowland basin depends on many factors, but a significant variable is the amount of meltwater and suspended sediments which are being produced by the ice. When runoff is relatively low, the ice advances in direct contact with the existing landscape. When runoff is high, a large outwash plain of sand, silt, and gravel is deposited by rivers in advance of the ice. The growing glacier then advances over this bed of sediment. When a continental-scale glacier retreats from a landscape, many factors influence the landscape it leaves behind. One significant variable is how fast the ice is melting. Meltwater accumulates at the base of the glacier and drains off in channels which parallel the direction of the ice flow. If the glacier is riding on a bed of sediments, faster melting results in a deeper erosion of the subglacial landscape. Between these subglacial meltwater channels, the intervening ridges are shaped by a continuing flow of the ice above. These characteristic meltwater-cut, glacially smooth ridges are known as drumlins. The upper left are drumlins left by a continental glacier near Auburn, New York. On the right is a LiDAR image of drumlins in the Seattle area. LiDAR imagery removes the vegetation and acquires a 3D map of the underlying topography. As a glacier finally retreats from the landscape, it deposits a layer of morainal debris known as glacial till. Glacial till is unique in that, unlike wind or water-deposited sediments, it is laid down as a uniform blanket across the existing topography. It is plastered on hilltops, valleys, and slopes, clinging even to quite steep hillsides. In this way, its surface mirrors the surface of the underlying substrate. As glaciers retreat from a landscape, a variety of other landforms can develop under suitable conditions. Several of these are common in the Puget Basin. Among the most common features are glacial erratics and kettles. Glacial erratics are large boulders which are essentially moraine features. These boulders can be as big as houses and can be transported hundreds or thousands of miles on the ice before being deposited as it retreats. Without an understanding of this process, these isolated boulders, often of rock type which are exotic to the area, are profound enigmas to the casual observer. Kettles are large depressions in the landscape left by stranded pieces of ice as the glacier retreated. Kettles develop best in settings where outwash streams from the retreating ice blanket the area, and in part the ice blocks, in an additional layer of sediment. When the stranded pieces of ice finally melt, they leave a distinct depression in the landscape. Sometimes these are occupied by kettle lakes. These are distinctive in that they typically have no outlet stream. Most of the modern landscape of the Puget Basin is due to the effects of the most recent glacial episode, the Fraser Glaciation, known locally as the Vashon episode. It commenced about 25,000 years ago and ended about 12,000 years ago. This episode ended the Olympia interglacial period, which started between 50 and 60,000 years ago. Pollen samples from the Olympia period reveal a climate not dissimilar to that which exists today, a setting dominated by coniferous forest of fir and hemlock. The sediments deposited over this period are known as the Olympia Beds, and they are fairly widespread occurrence along the eastern coast of the Puget Sound. They reflect deposition along rivers and bogs and in lakes, a landscape similar to that which exists today. Notably, there are no marine sediments in the Olympia Beds, which suggests that there was no Puget Sound over this period. Instead, the basin was apparently a vast river valley with an ancestral Puget River draining north to the Strait of Juan de Fuca. About 25,000 years ago, glaciers started growing in the insular mountains of Vancouver Island and in the North Cascades of Washington. In the Cascades, this is known as the Evans Creek episode of Alpine Glaciation. North of the border, the ice in Canada had coalesced into an ice cap by this date and was advancing to the south. The Cordilleran ice cap was several thousand feet thick as it advanced south down the Georgia Strait. North of the border, it advanced up the Fraser Valley, eventually blocking the flow of the very large Fraser River. The ice impounded a large lake in the Fraser Valley, which accumulated until it overtopped a divide at the head of the Columbia Valley, north of the town of Kendall on the Mount Baker Highway. This divide was breached in the early glacial episodes, forming the Columbia Valley Spillway. Darrington is in the northern Cascades in Washington. By 18,000 years ago, the ice had breached the Chuckanut Mountains south of Bellingham and spilled south into Skagit Valley. As the ice rode up against the Cascade foothills, it dammed the Skagit River, now also receiving the water of the Nooksack and Fraser. Once more, a large lake was impounded until it could drain south to the next drainage. Along a route cut in the early glacial episode, the water flowed south through the Sauk Valley to Stilgamish Valley. The Sauk Valley was cut through a low divide by floodwaters during the early glacial episodes. The combined floodwaters of the Fraser, Nooksack, and Skagit cut the great coulee of the Sauk Valley, which extends south to the headwaters of the Stilgamish River. This water then flowed west down the Stilgamish Valley. About 16,000 years ago, as the ice was advancing across the southern end of what is now Whidbey Island, it contacted the northeastern end of the Olympic Peninsula. As this happened, the ice formed a dam across the northern end of the Puget Basin. Behind this dam, the water of the Puget Basin accumulated rapidly. This included all the runoff from the adjacent mountains along with water draining directly from the ice front. This lake eventually rose to a point about 200 feet above current sea level, where it completely filled the bottom of the basin. This pro-glacial lake is known as the Glacial Lake Russell, after pioneering geologist Isaac Russell. Large streams emanating from the front of the ice carried huge amounts of gravel, sand, silt, and clay, the products of vigorous erosion in the upper reaches of the glacier. These streams now emptied out into the waters of Glacial Lake Russell. The silt and clay-sized particles were carried by currents out into the lake, where they slowly settled to the bottom. These lake bed clay deposits are known as the Lawton Clay, named after exposures at Discovery Park, Fort Lawton in Seattle. They accumulated on top of the Olympia Beds, and where those were absent, on older glacial and non-glacial sediments. Up to 150 feet, 50 meters of these clays and silt beds were deposited across much of the region. In places, these deposits are comprised of thin alternating beds of clay and silt, representing seasonal changes in the sediment composition. Back at the glacier terminus, the large quantities of gravel and sand being brought by these streams settled out quickly as they poured into the quiet waters of Lake Russell. These coarse sediments accumulated in a broad outwash plain, effectively a river delta in advance of the glacier. The vast sandur, to use the Icelandic term, extended for miles in front of the ice, a broad apron of sand bordering the ice front. This layer of sand and gravel was deposited on top of the Lawton Clay as the glacier advanced into Lake Russell. These proglacial outwash sediments are known as the Esperance Sand, named after a small community near Lake Ballinger, where they were first studied. This layer accumulated to about 150 feet or 50 meters in thickness, deposited on top of the Lawton Clay. This is a block of Lawton Clay at the cliffs along Double Bluff Beach, Whidbey Island. This clay was deposited on the floor of Lake Russell, accumulated from glacial clays brought by rivers draining from the glacier's terminus. The Esperance Sand on the bluffs at Discovery Park. The cross-bedded, locally trough cross-bedded character of the sediments is apparent. These sediments were deposited as a glacial outwash plain in advance of the ice by heavily burdened rivers emanating from the glacier's terminus. By 14,000 years ago, the Puget lobe had advanced to its furthest extent, a point just north of the town of Continental. By this point, it had completely displaced glacial Lake Russell. The ice was 6,000 feet thick over Bellingham and at least 3,000 feet over Seattle. To the west, another great lobe of ice extended out the Strait of Juan de Fuca, reaching to the Pacific Ocean. Along the margins of the Puget lobe, great lakes were impounded high up into the mountain valleys, some of which were only recently abandoned by local glaciers. Along the southern end of the glacier, meltwaters coursed through a network of outwash channels directly into the Chehalis drainage. The Puget lobe reached its maximum extent about 14,000 years ago, but does not appear to have held that position for very long, as evidenced by the retreat of the Alpine Glaciers in the Cascades several thousand years earlier. The climate had been warming for some time by this date. While the effects were not felt at the far terminus of the Puget lobe, the Cordilleran ice cap had probably reached a negative mass balance by 16,000 years ago. By the time the Puget lobe stopped its advance, it would appear that large-scale melting was already underway. The Puget lobe receded from the Puget Basin at a rapid rate, breaking up as its mass was thinned by rapid melting of the ice. Most of the modern landforms of the Puget Basin have their origins in this rapid melt-off of the Puget lobe. These events have left the region a mix of upland provinces, distinguished by prominent north-south trending hills, and a network of deep north-south trending channels which border these upland areas. In large part, these features are constructed out of the 300-foot thickness of proglacial sediments which were originally deposited in front of the glacier. The modern landscape largely reflects erosion into these layers of sediment. And I leave you with this beautiful image of the Puget Basin today.